Continuing from here, we've talked about the nature of these sources a little bit. Okay. Now, this circuit, for this circuit, it doesn't matter what omega is. Whatever it is has already been factored in. So what I'm going to do is say, let's just, as I continue my example, and I continue to try to, the goal of this is to tie it back to the nature of the sources that we're working on. So we're going to say soon, I'm going to say, well, let's just declare that omega is equal to 1 and see what happens. And we'll end up going from there. Okay, but depending on the value of omega, there are a lot of different values that the capacitor and the inductor can have. So the one that I'm going to continue with from here is the one where, oh, and you actually can't see that I wrote omega equals 1. If omega equals 1, we know that in an inductor, we know that the impedance of an inductor, is that visible? Yes, is j omega L. So if this inductor has an impedance of j omega, or of j, this is a capital omega because it's ohms, but if the impedance of the inductor is j ohms, it must follow the rule that ZL is j omega L. So if we knew that omega was 1, in which case these would just be straight up cosine of t, if omega is 1, we know that this inductor would have a value of 1 Henry in order to cause the inductance to be J times 1 to get J. And we also know that on the capacitor side over here, on the capacitor side, we know that the impedance of the capacitor is 1 over j omega c. And so the 1 over j is the same as minus j. So this is also minus j over omega c, where again, j is what we use instead of I in circuits for the imaginary unit, or I, yeah. So minus j over omega c. If omega is 1, we could conclude that the capacitor over there would have to be 1 farad, which is very unrealistic. A farad is huge. I mean, even a Henry is pretty large, but depending on the value of omega, we would get different values for the inductor and the capacitor. So if instead, let's say that omega was 3, then these would be 6 cosine of 3t and 2 cosine of 3t. In order for the circuit to look like this, that would happen if the inductor had a value of 1/3 Henry, so that j omega L would still be equal to j ohms. And if omega was 3, the capacitor would have to have been 3 farads in order for omega c to equal 1. If omega is 3, or no, we would need omega c to equal 1. So wait, so it's j omega L, and it's omega c. No, so it would have to be 1/3 of a farad as well, actually. Yeah, because you still multiply omega by the capacitance or the inductance. Yeah, so it would have to be 1/3 farad to still get a value of 1. Because we would need we would need omega c to equal 1, and we would need omega L to still equal 1. So depending on the value of omega, the value of the inductor and capacitor have to be different to have everything check out, right? As a result of the inductor and capacitor having different values, the coefficients that go in front of the derivatives and the time voltage characteristics of capacitors and inductors. So what happens is, it doesn't matter what omega is once it's drawn like this. There are a whole set of equivalent problems with different values of L, C, and omega that would all turn into this picture. So there's a omega can be anything from 0 up to, well, you can head in the direction of infinity, but the value of omega, for different values of omega, the inductance and capacitance would need to be different depending on omega to produce exactly this impedance AC version of the circuit. So we're not given omega up front, so it doesn't actually matter to us what the omega is here. If we want, however, to understand and think about what is truly happening in the circuit, we would need to choose an omega or know what the omega is usually, but since this is a made-up problem, it's just going to be omega. I'm just going to pick an omega. And so we're going to say that omega is equal to 1 now. We're about to cut the video in a second. Okay. So if omega is definitely 1, then we have a particular inductance and capacitance. And if we want to start looking at what our solution tells us about the nature of what's happening in the circuit, I'm going to declare omega to be 1. Therefore, the period t is 2 pi, which is not really going to matter to us here. We're just going to let the omega be 1. And so we just have to remember, I'm leaving the omega equals 1 to say, we're going to assume, just to make the problem so that we can tie it into a more realistic discussion, we're going to let omega be 1. So the period is just 2 pi. In that case, the capacitance would have to be 1 farad and the inductance 1 Henry. And so in this circuit, if I wasn't in impedance mode, if omega is 1, then I can say that the inductance, okay, which otherwise I wouldn't be able to see. So I'm just going to write in parentheses off to the side, this would need to be 1 Henry to get this inductance. And this capacitor would need to be 1 farad if omega is 1 in order to make the phasor domain of this start to look this way. So I'm going to cut the video, and then what we're next going to look at, I may unfortunately have to zoom the video out a little bit, which I didn't want to do, but you'll at least see it fairly close up in this version. So, okay, so I have to zoom the video out just a bit, but I'll try to write the rest of it large.